were forming downbursts which forms excessive forces on structures and transmission lines. The downbursts were the reason of maintenance towers that had built before, as reported by Manitoba Hydro in September 1996. For modeling and validating of the computational fluid dynamics data that for the downburst twin field, a large confining jet facility, there are tests conducted in it, and the numerical analysis formed to model the downburst wind profile, and there was an agreement between the test that was carried out and the numerical model. So computational fluid dynamics simulation were conducted by Hanger and Kiernan in 2004, and it was found that the wind field has its radial and vertical velocity components, and the parametric study conducted by Shahada et al. In 2005 showed that the vertical velocity components can be negligible compared with the radial one, and the radial velocity component normalized by the jet speed of the downburst, its maximum value is around 1.1, and it was decided that static analysis would be conducted rather than dynamic analysis because the period of the structure is much lower than the period of the load. And this figure shows the different parameters that are affecting the downburst configuration. It depends on the jet velocity at which the downburst hit the ground, the jet diameter or the size of the downburst, and the distance between the center of the downburst and the center of the tower, and the angle of inclination of the downburst event with respect to the tower. So the objective of the current research is to develop a numerical model to analyze the pre-stressed concrete transmission pools and incorporate this model to study the behavior of pre-stressed concrete transmission pools under downburst loading, knowing that these pools are mainly designed to remain upright under normal wind loading. During the development of the numerical model, Rodriguez and Boca modeled in 2001 for calculating the moment curvature diagram under specific compression forces is incorporated, and for every cross-section, the curvature under axial and bending stresses is determined, and this curvature is integrated along the height of the pool to determine the top deflection. For validating the section analysis for the developed technique, two different cross-sections or two circular hollow pre-stressed concrete sections are investigated for various outside diameter and inside diameter and various initial pre-stressing strain, and different number of strains and different stress area and different compression forces, and the moment curvature for each case is compared with the response 2000 program, and this shows that there is a big agreement between the developed technique and response 2000 program, so we can rely on the developed technique in the section analysis. So to verify the integration process along the pool height, there was a pool tested by Barney-Hall in 1994. It was 27 meters high, and the load top deflection curve is drawn experimentally by Barney-Hall, and the developed technique shows a big agreement with this load deflection profile, and there was a slight increase in the maximum load that can be sustained by the pool in the developed technique because nominal period factors were used, while there might be some deterioration in the load deflection in the pool that was tested by Fouad et al. So the steps of using the numerical model, we first read the computational fluid dynamics data, and then compute and scale the wind velocity on the tower and conductors for a specific downburst case, and then we will input the pool dimensions, tapering slopes, and strength properties such that this pool remain uncracked under a normal wind speed of 40 meters per second, and then we will calculate the induced forces and straining actions under this specific downburst case, and we will check if the section is adequate or not. If the section is adequate, we will draw the moment curvature diagram under certain compression force, and we will determine the total drift under this specific downburst case. And if the cross section is not adequate, so we will say that this pool is unsafe under this downburst case, even if it's designed to remain undragged under a normal wind speed of 40 meters per second. So a case study was used, 25 meters at Liverpool, and the cross-sectional dimensions are similar to Dye and Chen 2007. Arbitrary conductor properties were assumed, and the maximum span that the conductor can be extended such that the pool remains undragged under a normal speed of 40 meters per second is determined. According to that we have assumed arbitrary conductor properties, we don't know what is the exact span that the conductor can extend by. So a parametric study for the span of the conductor was conducted, and we determined the maximum span that the conductor can extend by, such that the forces coming or acting on the pool make it remain undragged under a normal wind speed of 40 meters per second. And after specifying this span of the conductor, we will use this pool of Dye and Chen 2007 and this conductor properties with the specified span to do our parametric study on downburst cases. So this is the pool dimensions. It's 25 meters high. The outside diameter at the top was 0.28 meters. The outside diameter at the bottom was 0.72 meters, and the top thickness is 0.14. The bottom thickness is 0.20. And here are the conductor properties. The handling point elevation was 23 meters. The diameter and the weight of the conductor are shown. Modulus of the used, and the sag of the conductor is 2% of the span, and the spans were ranging between 100 meters and 500 meters. So this slide shows the result of the parametric study for different spans of the conductor and the maximum normal wind speed that the pool can resist without being dragged. So when the span was 100 meters, or when the conductor span was 100 meters, the maximum velocity that can be, the maximum normal wind velocity that can be sustained by the pool without being dragged was 40 meters per second. And when the span increases till it reaches 500 meters, the maximum or the critical normal wind velocity that can be sustained by the pool to remain undragged was only 28 meters per second. So we decided to extend the conductors by 100 meters and use this conductor with this span to conduct our parametric studies on the downburst. As we mentioned before, the parameters of the downburst, the jet velocity was ranging from 5 meters to 70 meters per second, so we have 14 cases. The jet diameter was ranging from 500 to 1500 meters, total 11 cases. And R/D ratio ranges from 0.2 to 2. And theta ranges from 0 to 90, so we have 7 cases for theta. And a total number of 11,158 cases were studied. In each case, we calculate the forces on the conductors and the forces in X and Y directions on the pool, and we calculate the maximum bending moment acting from each case on this pool and the top deflection. So the results of the parametric study is shown here. The effect of variation of jet diameter is not very significant. When the jet diameter was 500 meters, it gives the most critical bending moments on the pool, and those curves are for different jet velocities from 5 meters per second to 70, and for a specific R/D ratio which was determined before by Shihata et al. In 2005 to be the critical one, which was 1.2. So the critical jet diameter was determined to be 500 meters, and those curves variation of the maximum bending moment coming from the pool with the angle inclination, which is theta, and it was found that when theta equals to 0, this is the maximum bending moment that can affect the concrete pool. And those curves ensures that what we have mentioned before in Shahad et al. Back to 2005, that the maximum R over D ratio was determined to be 1.2, and this is the critical one which causes the maximum bending moment that can affect the pool under TJ, which was verified to be the more critical 500 meters, and theta equals to 0 degrees. And to determine the maximum jet velocity of the downburst that the pool can sustain, it was found that the maximum jet velocity for the downburst was 65 meters per second. And here is the top deflection normalized by the height. It was found that the ratio at 65 meters per second jet velocity around 0.15 or more, so the top deflection can reach like 4 meters, and this indicates that the pool can become out of service under the effect of the critical downburst configuration. So the conclusion of the study, we can say that a new numerical technique is developed and validated to assess the behavior of cantilever pre-stressed circular concrete pools under downburst loading, and for a specific conductor span of 100 meters, it was found that the critical downburst configuration occurs when theta equals to 0, dj equals 500, and R over D ratio equals 1.2, and we can say that the total collapse, concrete crushing, or excessive deformation can occur in the considered pre-stressed concrete pool supporting the 100-meter conductor span if subjected to a downburst with a jet velocity equal to or greater than 65 meters per second, and this concrete pool was mainly designed to remain upranked under normal wind speed of 40 meters per second. At the end, I would like to thank NSERC and HighGround for funding this research, and thank Worcester University for giving me this opportunity to do the research, and thank Charlotte for giving me the opportunity to do the